our examples now, our questions now are about looking at taking volume, getting volumes where we're getting slicing again. But the difference this time is that we get shapes where our slices are not circles, but other shapes. And the first one we want to deal with is a circle, has a solid which has a circular base, but the cross sections are a square. So every cross section, so you can see the square there. So what we've got to do again is get our area of our cross section so we can get our rectangular slice, and it'll be a rectangular prism here that we're going to get, and then sum all the prisms together like we summed the circular disc. So except this time it's a rectangular slice there. So the idea is that we've got our XYZ base. So our area on the base is what we need to find, because we've got to deal with the x squared plus y squared equals to 9. Because again, we've got to get our area. So if we look at our area here, our thickness is in terms of x, because it's thickness is across the x-axis there. But also we've got to look at what's our two sides of our square. So, or one side, we're just going to get the other side, and it allows us to get the area. Now, if we pick a point x, we go across it to some point x, and we're going to go up to y there. Or sorry, we're going up to y because this is in the positive direction, and back to negative y down this way. But the distance there would be 2y, so that means the height would be 2y. So it allows us to get the area of our face, and then times the thickness of the slice there. And we've got our relationship between x and y as x squared plus y squared is equal to 9. So when we do that, there's our diagram of our cross section. We've got 2y on the base, 2y on the height. So the area formula doing that would be 2y squared. Okay, which would give us, if we put y as 9 minus x squared, or that you could write that as 4y squared, and y squared is 9 squared minus x squared. We could write it there because we want it in terms of x, because our thickness is in terms of x. So that's where we're going to get our formula, volume formula from, and then we can convert it to put it into the sum of those, which gives us our integral from minus 3 to 3, 9 minus x squared with respect to x. So keep our 4 out the front, integrate, get 9x and x cubed on 3, between minus 3 and 3, do our substitution, it gives us 144 units cubed. So again, the integration wasn't too hard. This time we've got our base as the semicircle again, so it gives us a relationship between x and y, and our diameters here are all semicircles. So really what we're going to end up with is a hemisphere. Makes sense. But we're going to do it by slicing. If we didn't have to do it by slicing, you wouldn't bother doing this formula. You'd just use the formula for a half a hemisphere. Now we've got our thickness of delta x because our slices are perpendicular to the x-axis, so that's why it's delta x. So we've got our point x there, and again our point down this way would be minus y, and our y coordinate this way would be positive y. So we cross x, down minus y, up y for this way, so you can see the value of x there. So that allows us to get our area of our cross section, because our radius there would be y. So to get our diameter is 2y, but our radius would be just y. And the area of the formula for that semicircle would be half pi times y squared. And again, y squared would be the 9 minus x squared. So the square root of 9 minus x squared all squared gets us to cancel. And because we put it back in terms of x, because it's going to be delta x. So in pi on 2 outside of 9 minus x squared, which again we do our integration between 0, minus 3 and 3, or in this case I've gone 0 to 3 and just doubled the whole area, and that gives us 18 pi when we go down and get that. This time we're staying with the same base, x squared plus y squared is equal to 9, but this time we've got an isosceles right angled triangle. So a hypotenuse there would be the 2y again, because that's our point x gone across x, y there, y in that direction. So 2y is our hypotenuse, and the other two sides are really what we need, because we know we got a right angle there. So that's what our diagram starts to look like. of our cross section. Again, it's perpendicular to the x-axis, this cross section, so it's going to be delta x. So from that, we can do this a few ways. We can use Pythagoras' theorem and say put a on both sides. That would equal 2y squared, so a ends up being root 2 of y. So we can get it that way. Or we can use trigonometry, because we've got a 90-degree angle there, so we've just used cos of 45 because it's isosceles. So we're able to get the side being root 2y. So the area formula then would be half of the base times the height, and they're both the same, so that's why we've got root 2y squared, and the half and the root 2 all squared would cancel, just gives us y squared, and we know y squared is equal to 9 minus x squared, because that's our relationship, times delta x. So again, there's our formula. We go 2 lots of it, because we're going from 0 to 3 instead of minus 3 to 3. 9 minus x squared comes down to 36 units cubed. This time we've got our solid base being x squared on 4 plus y squared, so it's an ellipse. And again, every cross section is a square one side of the solid. So again, we get across x. Our distances is y in each direction. So 2y along our base means 2y for our height. Allows us to get our diagram of our cross section, which our area would be 4y squared, and y squared is equal to 1 minus x squared on 4. So we get that, and we've put it back in x because we've got delta x. And then again, we're going to go from 2 lots of 0 to 2, because if we look at our x values, we're going from minus 2 to 2. So we go back, so we're going to make sure we have 2 lots of 0 to 2. If you want to go minus 2 to 2, it's fine. And 4 minus x squared, which is not a hard integral to calculate, and get our answer there. So there's how we start to do it with a base of a certain shape, and we start to get our cross sections of something different than the slices that were a circle when we rotate something around an axis. So we get, but the same idea, we get our area of our cross section multiplied by the thickness to give us our slice volume of our slice, and then be able to do the sum and use the integral to get our final answer.